We're going to look today at giant ionic lattices, or the giant ionic lattice. So let's think first of all about a very small grain of salt. And that salt has got the formula NaCl, which means it contains lots and lots of sodium ions and lots of chloride ions. And we've spoken in a previous video about how these ions are formed and the fact that they have charges. So I'm drawing them now in the arrangement that they would be in if we could look at a sub-microscopic level into this grain of salt. We would see lots of sodium ions and lots of chloride ions alternating with each other in a really big three-dimensional structure. So I've drawn just this in 2 dimensions here, but it would be in a 3-dimensional structure. So if I was going to draw a 3-dimensional cube here, we would expect to see ions arranged in 3 dimensions. And within those 3 dimensions, we would expect to see sodium ions, positively charged sodium ions, surrounded by negatively charged chloride ions, and then negatively charged chloride ions surrounded by positively charged sodium ions. And because of the arrangement of this 3-dimensional structure, we say that it is a giant lattice. The word lattice here is used to mean that it's a repeating structure. So within the lattice, there is a very strong attraction between our oppositely charged ions. So the positive charge on the sodium is attracted to the negative charge on the chloride ion and vice versa. And we say that this is a very strong electrostatic attraction or electrostatic force of attraction. And because of the strength of this electrostatic force, ionic lattices, ionic substances have very, very high melting points. So we have a high melting point, and that's because a lot of energy is needed to overcome this strong force of attraction. So lots of energy needed to overcome the force of attraction. Okay, so that's one of the properties of our giant ionic lattice, the fact that it has a very, very high melting point. And we need to be able to explain it in terms of the very, very strong force of attraction between the ions. There's another property we need to know about, and that's its electrical conductivity. So let's look at one of the situations where it will conduct electricity, and that is when it is a liquid. So I've got a battery here, and that battery is connected to 2 electrodes, one of which is going to have a positive charge, one is going to have a negative charge. And if I've got a liquid ionic compound in between there, it will conduct electricity. I'm just going to draw a few of the ions now. So a couple of sodium ions and a couple of the chloride ions. Because these ions are charged and because they are able to move, they can flow towards the oppositely charged electrode. So when a liquid, or when in a liquid state, the ions can move. And because they can move, they can carry a current or carry a charge. So they carry a charge and they move towards the oppositely charged electrode. Okay, so let's actually think about the circumstances under which an ionic compound will conduct electricity and when it won't. There's really only one circumstance where it won't conduct electricity, and that is when it is a solid. Because when it is a solid, the ions cannot move. They can vibrate, but they cannot move. So it can't, in this situation here, the ions cannot move to the oppositely charged electrode, so conduction will not take place. But as we said earlier, if we arrange or if we melt an ionic compound, which is going to have to happen at quite a high temperature because of the high melting point, then the ionic compound can conduct electricity. It can also do it when it's aqueous, and aqueous means when it's dissolved in water. So a way of representing this is to have the particles split up from each other, the ions split up from each other, and then surrounded by water molecules. So this is aqueous. It's unusual, but theoretically, a ionic compound as a gas can also conduct electricity because, again, the ions are able to move. There's a couple of other words we need to be aware of here. Liquid, sometimes we will refer to a liquid ionic compound as molten. And we use the word molten because it tends to happen at a high temperature, or melting tends to happen at a high temperature. Remember, aqueous here means dissolved in water. So just to summarize with these, conduction, electrical conduction, cannot happen with a solid. So solid ionic compounds do not conduct electricity. Molten, aqueous, and gaseous or gas ionic compounds do conduct electricity. And the reason is the ions are able to move and carry a charge. And if they can move, then the ionic compound will conduct electricity. Thank you very much.